wabarakatuh, and a very good day to everyone. Let's move on to the next topic, which is fugacity. Okay, is this the first time you heard about fugacity? Fugacity is the special features in chemical engineering thermodynamics. So let's get the concept into it first. Okay, so what is meant by fugacity? Basically, fugacity is the tendency to absorb and escape, right? So that is by right uh, the, the, the normal definition of fugacity. And I believe that by the the next definition, the fugacity means that it is a thermodynamic property of a real gas which, if substituted for the pressure or partial pressure in the equation for an ideal gas, give equation applicable to the real gas. Okay. Okay, so these are the learning outcomes. In with these equations, and whereby at constant temperature we get this one. Oh, sorry. So at constant temperature we get this one from this, and by integrating using a reference state for the partial molar Gibbs energy, it yields this equation and this equation, whereby the reference chemical potential is the chemical potential at the reference pressure and at the same temperature as the chemical potential of interest. Okay, so therefore, fugacity is defined as this equation equals to RT ln F fugacity I per fugacity naught, whereby this is the limitation to indicate it is ideal gas. Okay, fugacity can be thought of as a corrected pressure. Accordingly, fugacity has the units of pressure. So that's the relation. And the fugacity coefficient is, this is the unit. And this is the equation, right? Okay, there's one question. Why fugacity instead of chemical potential? Okay, so you can refer to the textbook, Koretsky, and refer to page 393 and give your answer in the comment section down below. Why fugacity instead of chemical potential, and what is the difference and what is the link one to another. And next one is the total solution fugacity, whereby this is the equation. So we have G minus G naught equals to RT ln fugacity per fugacity. After this, I will give one question on this. And the pure species fugacity. So please remember that this in bracket means that it's calling B always positive. And the criteria for phase equilibrium is F fugacity equals to fugacity beta alpha and beta. Okay, the concept of fugacity goes beyond gases. The defining equation is valid for an isothermal change from the reference state chemical potential to that of the system of all real species. The concept of fugacity is not restricted to gas phase. It applies to liquids or solids as well. So in this chapter, we will cover solid and liquid. Sorry, liquid and gas. So this is the diagram form for clear understanding. So the fugacity can be related to thermodynamic property data, whereby we can get from tables, equation of state, and generalized correlation. And but for the vapor, it can be according to reference state, whereby we have ideal gas, and it can be further derived into pure vapor and binary vapor mixture. For binary, we can use the Lewis-Fugacity rule. So according to the Fugacity coefficient. In the meantime, for the liquid, so reference state is the ideal solution, whereby we can use Lewis random rule and Henry's rule. It could be further derived into pure liquids and binary liquid mixture, and it can be further described through the activity coefficient as the equation follows. Okay, fugacity for gas phase, Lewis fugacity rule. So there are three levels of rigor. So we have one is full solution, whereby it is compositional dependent fugacity coefficient. Next one is first approximation, whereby it is fugacity coefficient based on pure species value, and the third one is second approximation by assuming ideal gas behavior. So this is the rule for the gas, and in the meantime, for the fugacity in liquid phase, we have to do reference test. The choose whereby we have two choices: Lewis random rule and Henry's rule. Okay, in this figure, we have fugacity of a binary liquid mixture. Also shown are ideal solution reference states based on AA interaction, Lewis random rule, and AB interaction, Henry's law. So this is the equation to relate or to correlate the behavior, and this is the Gibbs-Duhem equations to give the another relation in regards to the fugacity of a binary liquid mixture, whereby it can describe the interaction between A and B. Okay, fugacity in liquid phase, as previously mentioned in the diagram, it can be described through the activity coefficient. It is defined as the ratio of the value of the fugacity in the actual mixture to the fugacity that the ideal solution would have at the composition of the mixture. Okay. Please take note the difference between liquid, the behavior of the fugacity, especially the effect of vapor pressure in liquid and also in vapor. So the activity coefficient tells us how active the liquid is relative to our choice of reference state. Okay, total function and partial molar function, the Gibbs-Duhem equation. It provides a useful relationship between the partial molar properties of different species in a mixture, whereby it is a manipulation of property relations. And for example, if to find partial molar volume of species P and Vp in a binary solution, so we have Vp as a function of composition where it is known, then it's going to be described in this equation at constant pressure and temperature. Differentiate with respect to xa to get this equation, whereby a should be equals to 0, and divide by nt and rearrange and integrate will result to this further equation. The Gibbs-Duhem equation for activity coefficient. Another useful form of the Gibbs-Duhem equation is for activity coefficient. Writing it out for a two-component system, so after further rearrangement and derivation, so we can get this one. Since the chemical potential for pure substance 1 and 2 are constant, hold on. For constant, Plugging this result into the GT equation, it will give this equation. So basically this one refers to this. Hereby, this is also one important equation to describe the Gibbs-Duhem equation for activity coefficient. Okay, next one is we have excess properties. An excess property is defined as the difference between the real value of any thermodynamic property K and the hypothetical value it would have as an ideal solution at the same temperature, pressure, and composition, whereby K ideal. We want to come up with values for this amount to find the fugacity of the liquid phase. This can be achieved by using an analytical expression for excess Gibbs energy because there is a direct relationship between the partial molar of a species and its activity coefficient, which can be described as below. Models for using the excess properties, the excess Gibbs energy. So this one begins with the two suffix Margulis equations. After several derivation, we get this one, and then these are the list of common binary activity coefficient models. So you can refer to what kind of model that it is mentioned. For example, the question asks for you to come up with several models, then we can try to adapt it. And okay, so that's all for today. I'll see you next time. All the best.